Okay, let's get started. So this week we're going to be doing a new chapter, limits and continuity. So for this double, we're going to finish off on the introduction to limits. Later on in the semester, we'll come back to limits. So please don't learn and forget. We will see this in a couple of weeks again. Then continuity, we're going to do that tomorrow. Okay, so end of the week will be limits and continuity, and then that will be for the quiz next week. Okay. So for limits and continuity, there's like one equation that we're going to be looking at. You might have seen this before in high school, but like I said before, forget what you did in high school. We're going to start from the beginning to avoid any issues of, some being ahead, some being behind. Okay, and that is the limit equation. So we write it in the following way, LIM for limit. In the bottom here, we have x right arrow a. We'll see what that means in a bit. Then we have our function f of x. And we say that this limit exists and has a value. If we can calculate this left-hand side, get some value, we call that L, the limit value. Yeah. So f, that's our function. A, that is our limit point. Okay, and L, this is the limit value. Okay, you might hear it as limit value or limiting value. It means the same thing. It's the value of the limit. Okay, so please just take that down. That's the terminology that we'll be using later on. So if I say the limit point is this, you need to know what that means. If I say the function has a limiting value of 2, you need to know where that comes from. Okay, so how do we read this expression? We read it as x approaches a, the function approaches L. Okay, that's the idea. So we read this expression as x approaches a. For now, you don't need to know what that means. Just that's how we read it. So as x approaches a, f of x approaches L. Okay, now you don't need to know the details of what we mean by approach, but that's just how we're going to be saying it. Okay, so we'll start off with a little diagram to get the idea across. Then we'll look at some more complicated examples on this. Okay, so please keep this diagram in mind whenever we're talking about limits. And later on, when we talk about continuity, you have to have this diagram in mind. If you don't, you're going to be lost. Okay, so we've got some function, however it might look. Okay, we've got a function f, and we have a point of interest over here at a. Now, a is just some elements of our domain. Okay, so there. Later on, we'll see a doesn't have to be an element of the domain. But for this example, we'll say a is an element of the domain. We can look at what the function value will be. So here we have f at a. Okay. Then if we pick some other points, x, and that will have some function value f of x. Now, the whole idea of this limit is that on the right there, we see we have x. If we move x closer to a, you can see with your finger, you just go down along the function, it will get the function value will get closer to f of a. Okay. So that's the whole idea behind this limit. So again, it's just a very simple diagram to keep in your mind. We will be looking at much more complicated things, but this is what you need to think of. We have some points, fixed points a, x can move around. When x gets closer to a, the function value f of x gets closer to f of a. Okay. So this is a particular case of a continuous function. Continuous function. Okay, so it's nice and continuous. You have an idea of what that is from high school. But as we go through, we'll make that more technical. Okay, so in general, we can approach the value of a using x values that are less than a. Okay, so that will be coming in from the left. We can start from the left and move to a on the right. Or we can start with x values greater than a and move to the left. Okay, using x values greater than a. Okay, so in other words, there are two ways to approach our limiting point. We can approach from the left or we can approach from the right. That's going to give us two types of limits. We're going to have the left side limit where the values are less than a and the right side limit where the values are greater than a. I don't think you would have done that in matric, right? Left side limit, right side limit. Did you cover that? No. Okay. So here we're going to have the left side limit. Okay, so if we are on the left, we are using values less than a, and we write it in the following way. The limit as x approaches a with a little minus in the exponent. So that minus shows that these x values are less than a. So minus, we're on the left side. Okay, and we also have a right side limit. That's where we're using values that are greater than a. Okay, so we have the limit, x approaches a, and we put a little plus there to show that those x values are larger than a. Okay, so again, we have our point A. When we are taking the limit, or when we are approaching a, we can do so from the left side, where the values are smaller than a. We can do so on the right side, where the values are greater than a. That gives us two different types of limits. Limit from the left and limit from the right. Now, we say that the limit exists if the limit from the left is equal to the limit from the right. In some cases, they won't be equal, and we say that the limit does not exist. Okay, so the limit, as we wrote it here, over here, this limit exists if the left side limit and the right side limit both exist and agree. They must be the same value. So the limit as x approaches a, f of x exists. That's the word we use. So the limit exists if the limit as x approaches a minus, so the one from the left, exists and is equal to the limit as x goes to a plus, that's using values greater than a. Okay. Then whatever value we get for that, we assign that to the limit. So in other words, whatever limit question we get, in practice, we need to check both of those side limits in order for the limit to exist. Okay, so I'll give you a function, I'll give you a point. So say limit x goes to 2 of x squared, for example. In practice, we need to check the limit from the left, get a value, the limit from the right, get a value. If those values agree, the limit exists and it has whatever that limiting value is. If they do not agree, then the limit does not exist. Okay, that's what we write down. So otherwise, the limit does not exist. Okay, in other words, D and E, you might have seen that before. D and E does not exist. Okay, any questions so far? All good. And again, keep this diagram in mind with x being on the left or being on the right. Okay. So for these examples, please always keep this in mind. Okay, example. Let's say we have the following function, f of x is equal to x squared. If x is less than or equal to 0, otherwise it's 1 minus x if x is greater than 0. So we have a piecewise function, we have the split domain, negative values and 0, and then all of the positive values. You should have done plenty of this in the TUT on functions. Yeah, right, sketching it, finding values, all of that. That was in the previous tutorial. So let's sketch this first, just to get an idea of what we're working with. Okay, so at 0 and before 0, we're looking at that top part. That will be x squared. Okay, and we can put a big dot there. Remember, that means it's included. So big closed-in dot, we're including that point. And then to the left here, it's just a parabola going up to infinity. What about on the right? We see it's 1 minus x, so it's a line sloping down. We are not including 0, so that will be an open circle. Okay, not including. Okay, so here's 0, 0. There's 0, 1. That will be 1, 0. Just to label some points so we can see what's going on. Okay, everyone okay with the sketching? Okay. Now for the question, we want the limit as x goes to 0. Of our function. Okay. Does it exist? If it does, what's the value? Now, like we said, as soon as you see a problem with limits x going to something, immediately think left limit, right limit. So let's check. We're going to check the left one first. So that will be the limit as x goes to 0 minus. Then we'll check the limit as x goes to 0 plus, and we'll see if they agree or not. So we have the limit x goes to 0 minus of f of x. So this will be the limit as x goes to 0 minus. So remember, 0 minus, we are looking at values less than 0. So we look at our diagram, or we look at our function, values less than 0, are we looking at the top part or the bottom part? The top part. Okay, this is where the values are less than 0. Or if we look at the diagram, we're looking at this left part. So this will be limit x goes to 0 minus of x squared, because we're looking at the left side of the diagram. Okay, now what's that going to be? Well, same as we did before. We look at our diagram. We're going from the left side to 0, and we just follow the function, right? Like we had in the previous one. So x is going to 0. X squared is going to follow the function 0. Yeah, we just follow the function. So as x goes to 0 from the left, if we put a little dot on the function here, we see that the function is going down to 0 as x is going to 0. So it's 0. Now we need to check the right side limit. So this will be the limit as x goes to 0 plus of f of x. Now the little plus means we're looking at values greater than 0. So either we look at the diagram or we look at our function. If x is greater than 0, are we looking at the top part or the bottom part? The bottom part. So x is positive. X is positive also means this right side. So on the right side, we're looking at that straight line. So this will be equal to the limit as x goes to 0 plus. Again, we're looking at the bottom part. So that will be 1 minus x. Okay, same thing as before. We pick some value. And now we're moving from right to left on our diagram. So we follow the function. Where's that function going to? Follow the function. It's going up to? It can't be 0. It's going up. 1. It's not going to 0, right? The function value is going up to 1. So the limit value is 1. Yeah. Now we check. By the definition of the limit, the limit exists if the left limit is equal to the right limit. So here, the left limit is 0, the right limit is 1. So what can we say about the limit? Does not exist. So left limit does not equal right limit. Therefore, the limit does not exist. Right? Or you could put E in E for short, does not exist. Okay. Any questions for this example? Oh, good. Okay. So we can summarize what we've been doing so far. So we can say the limit as x approaches a, f of x is equal to L. Okay, so the limit value exists and has the value L if and only if. Okay, and then we have two conditions. Well, one condition with an and. So it's going to be limit x goes to a minus f of x is L, and the limit x goes to a plus f of x is also L. Okay, please put a big box around this. Okay. So again, the limit of the function as x approaches a is L if and only if the left limit and the right limit both exist and both have the value L. If one of them doesn't exist or they don't agree, then the limit does not exist. Okay. Any questions on this? Oh, good. Okay. Infinite limits and vertical asymptotes. So what do we mean by an infinite limit? Well, we write down the following. So if the limit as x approaches a minus, so we're coming in from the left side of f of x, is equal to infinity. We'll see what this means in a bit. So if the left limit goes to infinity and the limit as x goes to a plus, so now we're coming in from the right side of f of x is also infinity. Again, we'll see what this means shortly. Then the limit as x approaches a, so no plus or minus, just a, of f of x is infinity. Okay, so what do we mean by the left limit and the right limit being infinite? So we can see from a little diagram what we mean, and then I'll explain it technically. So let's say here we have x equals a. From the right side, we say that as we approach x equals a, the function becomes unbounded. Okay, so that's the name we use for this. So it becomes unbounded, which means that for any x value approaching a, the function is as large as you want it to be. Okay. And then we have the same thing on the left side. The function comes in, and as you get closer to x equals a, the function becomes as large as it can be. Right? It blows up to infinity. Okay. This is on both sides. Okay. So on the left side and the right side, the function becomes unbounded. Think of like 1 over x when x goes to 0. It becomes unbounded on both sides. We say that the limit is infinite, okay, because it blows up to infinity. And that line, x equals a, we call that a vertical asymptote. So the function f becomes unbounded Okay. And the line x equals a is called a vertical asymptote. Okay. Later on, we'll look at horizontal asymptotes and skew asymptotes. You wouldn't have covered that before. But for now, vertical asymptotes, it's a vertical line at x equals a, where on either side, we have the function going to infinity. Okay, so here the limit is infinite. Now we can have the same thing, where on either side, the function goes to minus infinity. So it's still an infinite limit, but now it's in the other direction. So if the limit x goes to a minus of f of x is minus infinity, it's still unbounded, but now in the negative direction. And the limit x goes to a plus of f of x is equal to minus infinity again. So on both sides, it's minus infinity. Then the limit as x goes to a of f of x is minus infinity. Okay. And again, we can have a similar picture. On the left side, it's going down to minus infinity. On the right side, it's going down to minus infinity. So we say the limit is minus infinity. Okay, so we have x equals a. Okay, on the left side, it's going down. On the right side, it's going down. Okay, so on both sides, it's going down to minus infinity. So the limit is minus infinity. Okay, now, please don't think that it just has to be infinite on both sides, plus or minus infinity. If we see this example over here, for 1 over x, on the right side, it's going to plus infinity. So you think, okay, the limit is infinity. No, look at the left side. The left side limit is minus infinity. The left side limit is minus infinity. The right side limit is plus infinity. Do the limits agree? No, the limit does not exist. So please keep these 3 pictures in mind. So number 1, both the left and the right go to plus infinity. Both the left and the right go to minus infinity. In those cases, the limit is plus infinity or minus infinity. In this third case, the right limit is plus infinity, the left limit is minus infinity, the limit is not infinity, the limit does not exist. Okay, so please keep those 3 cases in mind. All right, any questions on infinite limits? Yeah. It will be some a, yeah. Yeah. So these examples, it's just one vertical asymptote at x equals a. You might have more, but it will always be some x equals a for vertical. Yeah. Yeah, it will be y equals something. We will cover that later on. Okay, any other questions? All good. Okay, let's have a look at a few easy limit examples. So we'll do 3 of them. And then in the tutorial, there's like 50 for you to practice. Yeah, so you'll have plenty of practice with these. Okay, example number 1. We have the limits x goes to 0, 1 over x squared. Okay, now remember, there's always some hidden thing here. We write limit x goes to 0. So when I say evaluate the limit, it's always evaluate the limit if it exists. There's always a possibility that the limit might not exist. If that's the case, in the assessments, you are required to write down why. Okay, so just keep that in mind. So if the limit doesn't exist, you don't just write does not exist. You need to explain why it doesn't exist. Okay, I always add that onto the questions. Okay, so it will be evaluate the limits if they exist. Right, there's always a possibility they don't. Otherwise, explain why they don't exist. Okay, so please don't get shocked in the quiz or test when you have to explain, why it doesn't exist. Okay. So number one, we'll just go through these quickly. So limit x goes to 0 of 1 over x squared. Again, we need to look at the left and the right. So limit x goes to 0 plus. So we're looking at the right side. What happens when x goes to 0 on the positive side? The denominator becomes small, so the fraction becomes. The denominator is small, the fraction is large, right? Gets larger. So as x goes to 0, the fraction goes to. What's that? Yeah, it gets bigger. But as it approaches 0, remember, it's a limiting process. It's not, substitute a value. So as x goes to 0, the fraction goes to. Okay, sketch a picture of this. So 1 over x squared. Draw a quick little diagram of what that looks like. No calculators. No. You start using your calculator for sketching limits, you run into issues. Yeah. Because I see some people put, x equals 0.001, and they're drawing this massive line on the page saying it's 100 million or something. Yeah, don't do that substitution stuff. You'll run into problems. Okay, quick sketch. What do we get? Okay, think of 1 over x, right? Your hyperbola. So x is positive. As x goes to 0, the fraction gets larger. What is that going to look like? Putting pumps. They'll put the pumps. They'll confuse you. Okay, as soon as you start putting points and trying to connect the dots, you're already lost. Okay. Anyone thinks they got it? Maybe I should do the points again. It worked well last time. Okay, let's say 2 points, whoever gets the correct diagram first. What was the question? I'm not repeating that. You must listen. Okay, if you don't listen, you don't get the 2 points. Simple. Okay, your hands up. Yes. Yeah, very good. Okay, extra 20% for the next quiz. Okay, you play along, you get your points. You don't play along, you don't get the points. Simple. Okay, good. So it's going to look something like this. So we have x and y. It's going to look something like that. So from the positive side, you just follow the arrow. As x goes to 0, the fraction gets larger. The closer to 0 you get, the larger the fraction is going to be. In other words, it's unbounded, and so it goes to positive infinity. Right? Like I said at the beginning here, there we go. The function becomes unbounded because you can make the bottom as small as you like, so the fraction becomes as large as you like. That's the definition for unbounded. Okay, so that's on the right side. The limit on the right is positive infinity. Limit on the left, same thing. You follow from left to right. As the denominator gets smaller, the fraction gets larger. It's unbounded. It goes to plus infinity. Does the limit on the left and right equal? Yep, both of them are plus infinity, so the limit is plus infinity. Okay, example 2. We have the limit as x goes to 3 plus. So now we're only looking at the right side limit, not the left side limit, because we've got a plus there, of 2x over x minus 3. So we're looking at what happens to this function when x goes to 3 plus. So we're looking at values larger than 3. Whatever we're looking at in terms of x is always larger than 3. So in the bottom part, if we take something larger than 3 and we subtract 3, what do we get? Some positive number, right? Because it's larger than 3. We can have 5 and then 4 and then 3.5. It's approaching 3 greater. In the top, if we substitute something that's larger than 3, is it positive or negative? Positive. So the top is positive, the bottom is positive. Okay, we know that. Now, what happens when x gets closer to 3? What happens to the bottom? It's positive, we know that. So x is larger than 3. The bottom is definitely positive. But what happens when x gets closer and closer to 3? Okay, if we put 4, what do we get? What? If we put 3.5, a half is getting smaller. If we put 3.25, a quarter, the number's getting smaller and smaller. So what's happening to this denominator as we get closer to 3? It gets smaller. Okay. So if the bottom part is getting smaller, okay, the top part is going towards 3. So the top part is going closer to 6. The bottom part is getting as small as we want it to be. So 6 over something very, very small. What's that going to be? It'll be very big. So in the limit, it will be bottom gets very, very small, fraction gets very, very large. What happens to the fraction? So, yeah, and we say it's, if it gets very big, it's what? Look at the terminology we've been writing down. I underline things for a reason. Unbounded. Okay. If I underline it, it means the word is important. We need to be using these words. It becomes unbounded. Yeah. So the limit is, it's a unbounded positive number. So the limit is positive infinity. Good. Okay. Please get used to the terminology, right? Bounded, unbounded. You need to know these things. Okay. Number 3. Very similar. X goes to 3 minus of 2x over x minus 3. So we're going to do the same thing, but now x is going to be less than 3. Okay. So again, let's look at the bottom part. We have something that is less than 3, smaller than 3, minus 3. Is the bottom positive or negative? Negative. We are taking something smaller than 3. We are subtracting 3. It becomes negative. In the top? No, not negative. We are something smaller than 3. I never said less than 0. So less than 6. Thank you. Okay, so the top will be less than 6. Positive, right? It's positive. So the top is something close to 6. The bottom is negative and getting smaller. Yeah. So we have something positive over something negative that is very small. We take a fraction, we divide it by something very, very small. It becomes, stop using bigger, unbounded. That's the words. Okay. Okay. Baby school, things are bigger. We say unbounded. Okay. It's unbounded. But the bottom is also negative. So if you have something positive divided by something negative, the result is negative. So the limit is negative infinity. There you go. Nice. Okay. Number 4. We have the limit as x goes to 3 minus of 2 over x plus 3. And we go through the same thing as before. Look at the bottom. We are approaching 3 with the little minus, so it's less than 3. So we have 3 plus something less than 3. What's that going to be? 3 plus something slightly smaller than 3. There's a lot of incorrect mumbling. Okay. So 3 plus 3 is? Now it's slightly less than 3 that we're adding on. It will be something less than 6. Okay. So we have 2 over something less than 6. So in the limit, it will be 2 over. We're approaching 3. So 3 plus something getting very close to 3. It will be 3 plus something slightly less than 3, you said was slightly less than 6. So in the limit, it will be okay. What's 3 plus 2? 3 plus 2.5. 3 plus 2.75. What are we approaching? We're approaching 6. So what does the bottom become? We had 5, 5.5, 5.75. What are we getting closer to? 6. So in the limit, the bottom becomes? You said the answer already. In the limit, okay, come. In the limit, it becomes 6. Come, look at the definition we said here. Where's this? As x approaches a, f of x approaches L. Right. The bottom part was approaching 6. So the limit is 6L. That's the limit. So 6, yeah. Okay. So let's go through it one more time. So we have something slightly less than 3. X goes to 3 minus something slightly less than 3. So we have 3 plus something slightly less than 3. So it's something slightly less than 6, right? In the limit, it won't be slightly less than 6. It will be? It'll be 6. That's the limit. Okay. So we can have here, right? We had 5, right? If x is 2, it was 5. Then we had 5.5. Then we had 5.75. We can get closer to where we want. 5.95. The limit goes to 6. So that's the limit value for the bottom. Does everyone see that? Okay, so x is getting closer and closer to 3. So x plus 3 is getting closer and closer to 6. That's the limit value. Okay, so we have 2 over 6. That is, just to simplify, 1 over 3. Yeah. Okay. Is everyone okay with these examples? Okay, please make sure you understand this process. So x is going to 3, so x plus 3 goes to 6. Okay. Next, we have the limit laws. Okay, so we won't be proving these. There is a way to prove them. It's a bit out of our scope. So we're just going to write the laws down. We're going to use the laws, but you will not be asked to prove any of these. Okay, so you just know them. You do not need to know how to prove them. Later on, there will be a lot of proofs coming up. These ones you don't need to worry about. Okay. So suppose the limit as x goes to a of f of x. Now, as soon as I write this down, what do I mean? Limit x goes to a. What does that mean? No, that's how you read it. What does it mean? I write this down. What must we check? As soon as we have a limit like this, we must check 2 things. What's that? Exactly. Okay, please. As soon as you see this thing here, limit x goes to a f of x, immediately in your head, left limit, right limit. Every single time you see this. Okay, if you forget it, you're not going to get it, right? Okay, so please, as soon as you see this, immediately start thinking left limit, right limit, they must agree. They have some value L, so the limit value is L. So limit x goes to a minus is equal to limit x goes to a plus. They agree, they have a value L, so this limit is L. Okay, if you're not thinking this, you're not going to get it. Okay, always think about that. Okay, so suppose the limit x goes to a of f of x exists. We know what that means for it to exist. Look at the pink cloud. And the limit x goes to a of g of x exists. Again, the word exists, we know what it means. Again, look at the pink cloud. Okay, so we have the limit x goes to a of f of x exists. We know that, it's given. The limit x goes to a of g of x exists. We know that, it's given. Okay, so what can we do with this? So number one, the limit as x goes to a of f of x plus g of x. Okay, so we have the limit of a sum. If the two limits on the inside exist, then we can write the following. Limit x goes to a f of x plus the limit x goes to a g of x. Looks very simple, but please remember the cloud. Okay, so here, if we have the limit of a sum, if both of those limits on the inside exist, then we can separate it into two individual limits. Or if you go the other way, if you have two individual limits, you can put them together into one limit. If both of them exist, there's always that catch. Okay, number two, similar thing, but instead of a sum, we have a difference. So we have the limit x goes to a, f of x minus g of x is equal to the limit x goes to a, f of x minus the limit x goes to a, g of x. Okay, similar to before, there's a few more. So number three, limit x goes to a of some constant times f of x. The constant is not affected by the limits. We can take it out of the limit. So this is c times the limit x goes to a of f of x, where c is some real constant. Okay, number four. If we have the limit x goes to a of f of x times g of x, again, the limit of them separately must exist. Then we can write it as the product of the limits. Yeah. Number five, limit x goes to a f of x over g of x. Again, if they separately exist, we can write this as the limit x goes to a of f of x at the top, divided by the limit as x goes to a g of x. But here we have another condition, that bottom limit cannot be zero, right? We don't want to be dividing by zero. So on top of the two of them separately existing, the bottom one cannot have a limit of zero. Number six, limit x goes to a of our function f of x to some power n, whatever n might be. Okay, so what we can do is we can take the limit inside brackets and have the whole thing to the power n. Yeah, so the limit can jump inside the brackets like that. Or if you have the limits inside the brackets, you can take the limit out. Okay, you can look at it both ways. Okay, number seven. limit x goes to a of some constant. Constants are not affected by the limit, so this is just c. Okay, and finally, number 8, the limit as x goes to a of x is just a. Yeah. We can see that very clearly with the diagram. So if we just have the function x, so just right down the middle here, whatever value you choose for x, the y value is the same. Okay, and it's along the whole line. So positive values, negative values, you just get the value back. Yeah, so you put in a, you get out a. Okay, very easy. Any questions on the limit laws? Okay, please make sure you have these written down. We'll be using them later on for evaluating the limits. Okay, again, you won't be asked to prove any of these. We just take it as given, but you will need to know them. They won't be given to you. There's no formula sheet or anything like that. Okay, later on when we do continuity and we have the continuity laws, those might be tested. Okay, these ones, no, you can leave out the proofs. Okay. Any questions before we move on? Yeah. Constants. 2, 3, 4, some number. Yeah. Okay. Any other questions? You're all good. What? Oh, sorry. Now, wave your hand if I can't see. Yeah? Yeah, so n is the exponents on both sides here. Yeah, n is any power. Yeah. Whatever you want. Any power. It can be half, 2, 3/2, whatever power you want. Yeah. -1, whatever your favorite number is. Yeah. Any other questions? Yeah. The power one. Okay. Oh, we can do an example. Let's just do an example underneath here. Okay. Let's say we have the limit as x goes to 2 of 1 plus 3x plus 2x squared to the 5. We've got some function in brackets. We've got a 5 as the exponent. So what this rule tells us is that the limit on the outside can jump inside to become the limit on the inside. So we can write this as brackets limit x goes to 2, 1 plus 3x plus 2x squared to the 5. So we can ignore the exponent and the limit can just jump inside. Okay. Any questions on that? All good. Okay, so here we say the limit just jumps inside. Okay, let's have a look at some more examples. Okay, and again, it goes evaluate the limit if it exists. If it does not exist, explain why. Yeah, that's how the questions will be. So number 1, we have limits as x goes to 2 of 2x squared minus 3x plus 4. So we're going to do this one in a lot of detail just to show you every single step. But in practice, please do not show every single step, right? You can skip some things. Okay, but for the first one, I'll show you every single step we do. Later on, you can skip it once you know what to do. Okay, so firstly, we have the limit and we have a sum and difference of things. So we're going to use law number 1 and 2 to split it up into individual limits for each of the terms. Okay. Does everyone see that for the first bit? So we have a sum and difference. So we're going to split it up into individual ones using limit law number 1 and limit law number 2. Does everyone see that? Okay. Now we are going to use limit law number 3 to take out any of the constants that are multiplying the terms. Okay, so limit law number 3 we're going to use now. Okay, so for the first one, 2 is a constant, we can take it out of the limit. 3 is a constant, we can take it out of the limit. Okay, everyone see what we did there? Okay, next, we have the limit as x goes to 2 of x squared. So we have something squared. We've got a power. So what we're going to do is use limit law number 6 with n being 2. Okay, everyone see that? Limit law number 6 with n being 2. Okay, just have a look at it and then see what we did with the limits going inside the brackets. Minus 3, limit x goes to 2 of x, plus the limit x goes to 2 of 4. Okay. Now, for the first term and the second term, we are going to use limit law, there we go, number 8. So limit law number 8 says that the limit as x goes to a of x is a. Okay, so for terms number 1 and 2, we are using that last limit law. So this is going to be 2 times the limit as x goes to 2 of x will be 2 minus 3. The limit as x goes to 2 of x is 2. And finally, the last one, we're going to use limit law number 7. The limit of a constant is just the constant. So the limit of 4 is 4. Okay, so this will be equal to 2 times 4. Will be 8 minus 6 plus 4. You get 6. Okay, so everyone see the steps that we followed? Okay, so each step we just used one of the limit laws to get to the next step. Okay, number 2. 2, we'll leave this for homework. You can try it out. Again, yeah? I did say them. Okay, so the first 2, I used limit law number 6. 6 and 6. Then we used number... Yep, sorry, that wasn't 6. That was 6 and 6. Taking out a constant, that was number 3. Okay, then we did the limit of x, that was number 8. Okay, and then the limit of a constant, that was number 7. Okay. Any other questions before we carry on? Oh, good. Okay, so next one. So we have the limit as x goes to minus 2 of x cubed plus 2x squared minus 1 over 5 minus 3x. Okay, so you're going to go through it exactly the same as we did number 1, using all of the limit laws. So we have the limit of a quotient. We can do the limit of the top and the bottom. Then we can separate the terms, use that power rule, take out constants, and so on. So show every step see what this limit value is. Okay, so this will be for homework. Okay, number 3, we have the limit x goes to 1 of x squared minus 1 over x minus 1. Here we have a slight issue because the limit of the top and the bottom, what's that going to be? So a limit of a quotient, we can do limit of the top and limit of the bottom using number 5. Okay, limit of the top and the bottom. But what happens with that bottom one? What would the limit of the bottom be? What's it? Hi, yeah?
Yeah, so
Okay.
Yeah.
Okay. Yeah, sure. Okay. So the limit for the bottom, what is that? When x goes to 1, the bottom becomes? Not undefined. It's the bottom. X minus 1 when x goes to 1. Ignore the top part, the bottom. Limit x goes to 1. So x is going to 1 of x minus 1. 0, thank you. Okay, the bottom part's going to be 0. What did we say was an issue when we used limit law number 5? The bottom cannot be 0. So we need to do something about that. Okay, so what we're going to do, notice the top is a difference of squares, x squared minus 1 squared. So we're going to write this as the limit x goes to 1, x plus 1, x minus 1 over x minus 1. Okay, please remember your algebra. X minus 1 over x minus 1, there you can go. So this becomes the limits x goes to 1 of x plus 1, and this will be limit as x goes to 1 of x is, yeah, the whole thing's 2, but limit x goes to 1 of x is 1 plus 1, we get 2. Okay, good. So please remember your algebra stuff from before, right? So you got a difference of squares and so on, difference of cubes, you're going to have to factor them, right? So please, factoring squares and cubes and all of that, please make sure you know that. So factoring squares and cubes. Right, a cubed plus b cubed, a cubed minus b cubed. Do you know how to factor those? No? Okay, please learn it. Okay. Number 4. This will also be for homework. You can try it out. So we have the limits as x goes to 0 of roots x squared plus 9 minus 3 over x squared. Okay. And I'll give you a hint. Conjugates. Right, remember your surds from high school? So multiply top and the bottom by the conjugate, and then you can get rid of that root. You don't know what conjugate means? Go home, Google it, and then try this out. Okay. Otherwise, you can look at tutorial number 1 on algebra. That covers conjugates as well. Okay. Any questions for this homework? Okay. And then number 5, we'll do in class. So we have the limit as x goes to 0 of absolute value of x over x. Okay, so here we have an absolute value. What we're going to do is write this as a piecewise function. Okay, we'll make it a bit easier to look at the left limit and the right limit. Because remember, limit x goes to 0. What does that mean? Limit from the left, limit from the right. Especially when we have piecewise functions. Very, very important that you look at limit from the left and limit from the right. Okay, so absolute value of x as a piecewise function, we can write that as x if x is greater than or equal to 0. So if it's positive, we just leave it alone. If it's negative, we need to multiply by a minus. Okay, that will always give us a positive value. Any questions on this? Okay, you should have covered this in the TUT on functions. Okay, there was a lot of this piecewise functions there. Okay, now what we want is not absolute value of x. We want absolute value of x over x. So we just divide by x. So the absolute value of x over x is going to be equal to, in the top, x over x, that's just a plus 1. And minus x over x, that's a minus 1. Okay, now let's look at the limit from the left and limit from the right. So limit from the left, we're looking at x values less than 0. What's the limit value going to be? So from the left, if x is less than 0, where does the function go to? It's one of those two. Take a guess, 50-50. Plus 1. Okay, if x is less than 0, less than 0, minus 1. If x is greater than 0, which one? Top one. Okay, and we can see that in the picture as well. So if you don't like looking at the equations, you can draw a picture to see. So if x is greater than 0, we're looking at the top part. So it will be something like this, plus 1. And if x is less than 0, that's on your left there, that will be minus 1. Okay, an open circle, right? Top one is closed circle because it's including. Bottom one, open circle, we are not including. So if we're looking from the right going left, it will be plus 1. If we're on the left looking right, it will be minus 1. So does the limits exist? No, right? We have two different values. The right limit was plus 1. The left limit was minus 1. They don't agree, so limit does not exist. Yeah. Any questions? Okay, so again, you can either just go from the equation if you want to work like that, or you can draw a picture if you want to work like that to see what the limits are going to be. Right? It's up to you. Okay. Any questions before we move on? Yep. Yeah. So the reasoning would be limit x goes to 0 minus does not equal. So you'd say limit x goes to 0 minus does not equal limit x goes to 0 plus. That's the reason, because they don't match up. If you want to write it in words, that's fine, but this is much quicker to write down. Okay. Any other questions before we move on? All good. Okay, last thing for today, the squeeze theorem. Also known as the sandwich theorem, depending on where you're looking. In the Stewart textbook and the lecture notes we're writing now, we're going to call it the squeeze theorem. If you look on Wikipedia and some other YouTube channels, you'll see it as the sandwich theorem. Okay, it's the same thing, just two different names. So I don't think it's, two different things you need to learn. Okay, so the squeeze theorem, as we're going to be calling it, or the sandwich theorem if you're looking elsewhere. Okay, strange name, but we'll see why it's called that in a little bit. So let's say we have three functions, f, g, and h, in the following order. So we're going to have f at the bottom, then we're going to have g in the middle, and h on the top. Okay, it must be in that order, otherwise you're going to get things wrong. Okay, so f at the bottom, g is in the middle, h is at the top. Okay, And we are interested in this point over here at x equals a. So what we want to do is find the limit as x goes to a of g, the middle one, and we're going to use the top ones and the bottom ones to help us out. Okay, so we have f of x at the bottom is less than or equal to g of x in the middle, which is less than or equal to h of x at the top. Okay, so you must keep that ordering, f less than g less than h. And the limit as x goes to a of the bottom one is equal to the limit as x goes to a of the top one, that's h. If these are both equal, so they exist, they have the same value, let's call that L. Then the limit as x goes to a of the middle one is also L. Okay, so this is why we call it the squeeze theorem. So G in the middle is squeezed between F and H. We can see that from the picture here. So G is squeezed in the middle of F and H, and we see here G again is squeezed in the middle between F and H. So if those outer two have the same limit value, then the middle one is forced to also have that limit value. Okay, it's squeezed to have that value. And also a sandwich, because we have a sandwich, top bread, G's the filling, another bread, something like that. Okay, but we're going to call it the squeeze theorem, right? If you want to call it the sandwich theorem, that's fine. But the textbook and what we're going to be using is the squeeze theorem. Any questions so far? Okay, so again, we've got F, G, H in that order. F and H have the same limit, and since G is being squeezed between the two, it's forced to have that limit as well. Okay, let's have a look at an example. So we'll have a look at two examples. One is not so bad, the other one is very geometric. So I hope you remember your circle geometry from last year. Okay, if you don't, please catch up in the next 10 minutes or so. Okay, so example number 1, show that the limit as x goes to 0 of x squared sine 1 over x is equal to 0. Now here, we can't use our limit laws of splitting this in two parts. Why? Well, if we look at the limit of the first part, x squared, that limit will be 0. Okay, that's fine. But we need both parts to exist. If we look at the second part, the limit as x goes to 0 of sine 1 over x, that's undefined, right? Because if x goes to 0, 1 over x, that goes to infinity, that limit does not exist. So we cannot split this into two parts. So this is not equal to the limit x goes to 0 of x squared times the limit x goes to 0 sine 1 over x, right? Because to split it up, we need both of those. Can you see the red? No. Okay, let's rewrite that in pink. You can see the pink. Okay, so this is not equal to the limit x goes to 0 x squared, limit x goes to 0 sine 1 over x. Why? Well, the first limit does exist, that's fine. The second limit does not exist. We need both of them to exist to split it up. So we cannot use the limit laws. Okay, so instead we use something else. We're going to use the squeeze theorem. Why is the squeeze theorem a good idea? Well, sine of x, sine of 1 over x, or sine of theta, is a trig function, right? Like cos. It's always bounded between -1 and 1. Always. Whatever the input is, it is always between -1 and 1. It is squeezed between -1 and 1. That gives you a starting point for the squeeze theorem. So we know that minus 1 is less than or equal to sine of 1 over x. Whatever that input is, doesn't matter. Sine of anything is between minus 1 and 1. Okay, so that's our starting point. Now we want to do the squeezing. So we don't want sine of 1 over x. We want x squared sine. Yeah? Why? What? Which? You can't use the pink one. What happens when x goes to 0 with 1 over x? Look at your hyperbola. When x goes to 0, 1 over x goes to? Look at your parabola, hyperbola. So this one. When x goes to 0, it goes to? It's unbounded. It goes to infinity. Can we do sine of infinity? Wow. It just oscillates, right? There's no sine of infinity. So there is no limit. Okay, think of it like this. So we have the sine function. It does that always. All the way to infinity, it oscillates. Is there a value at infinity that we can assign to it? No, it goes minus 1 plus 1, minus 1 plus 1, all the way to infinity. There is no limit to it. Do you see that? Yeah. So when when 1 over x goes to infinity, sine just goes between minus 1 and 1. There's no limit value. Okay, so we have this. Now we want to do the squeezing. So we want x squared sine 1 over x. So let's multiply through by x squared. Okay, so the middle is now our function that we're interested in. And on the left and the right, we have simple functions that we can take the limit of. Does everyone see that? Yes? No? Yes. Yes. Okay. So let's take the limit throughout, and then we're going to use the squeeze theorem. So here we have the limits x goes to 0 of minus x squared is less than or equal to the limits x goes to 0 of x squared sine 1 over x is less than or equal to the limits as x goes to 0 of x squared. Okay, so we've set up the limits. Now let's check if this is squeezed between the same values. Let's look at the left. Limit x goes to 0 of minus x squared. What is that going to be? We've got a parabola. We're looking at the origin. What is it? 0. On the right side, we have a parabola. We're looking at the origin. It will be? So on the left side, we have 0. On the right side, we have 0. This inside part is squeezed between 0 and 0. So what's the value going to be? 0, right? 0 from the bottom, 0 from the top. It has to be 0. So the limits x goes to 0 of x squared sine 1 over x is 0 by the squeeze theorem. Okay, because the upper limit was 0, the bottom limit is also 0, so it is squeezed between 0 and 0. It can only be 0. Okay. Any questions for this one? Yep. Yes. Yeah, that would be better to have the reason given. Yeah. Okay. Yeah, I prefer you to put the reasoning throughout, because if you screw up the calculation, at least I can give you 1 mark for knowing what to do. If you write nothing and you screw it up, can't help you. So it's more for you to get some part marks than it is for the actual calculation. Okay, I'd rather not give you 0 if you have something written down. Any other questions? Oh, good. Okay, example number 2 with the squeeze theorem. And for this one, please put a massive star, maybe another one, exclamation mark, exclamation mark, exclamation mark. So we will see this again in 1 week. Okay. Now, last year, I said, please put lots of stars, a lot of exclamations. We're going to be needing it later. We get to the next week, everyone's forgotten it. Now we have to do it again. I'm not going to be doing it again. We're just going to move on. So please put lots of reminders here. You have to know this limit for when we do differential calculus next week. Okay. Please make sure you remind yourselves. Okay, so here we have show that the limit x goes to 0, sine x over x is 1. Very, very important for when we do differential calculus. Please make sure you know how to do this limit. Okay, so we can't split this up into parts like we had last time. If we have the limit of the top and the bottom, what happens to the bottom? Limit x goes to 0 of x is 0. The bottom is 0. We cannot use that limit law, right? We go back up a little bit here. Limit law number 5, the bottom cannot be 0. If it's 0, we cannot use the limit law. We must use something else. Over here, the bottom will end up being 0. We cannot use the limit laws. We must use something else. We're going to use the squeeze theorem. So we cannot use the limit laws. We will use the squeeze theorem. Sorry, we will use the squeeze theorem. Okay, now there's a number of ways of proving this. This is just one of the ways. Okay, if you have another way, that's perfectly fine. Use that. But we're going to use some circle geometry to set up those bounds, right? So f less than g less than h. We're going to use some circles and some areas to have one area less than or equal to another, less than equal to another. Then we'll do the limits. Okay, so let's set up the geometry for this. Okay, so we're going to have a circle. It's going to be a unit circle, so radius 1. And then we have the following construction. So it's going to look like this. We're going to extend this outwards to a tangent. Okay, so it's tangent at that point at the bottom there. We extend this other radius past the circumference until it touches the tangent. Then the intersection of that radius going out to the tangent, we're going to drop down to make a perpendicular line. Like so. Okay. Everyone with me so far? Okay. So again, we've got a radius going outwards horizontally. That's going to meet up with a tangent. Then this other radius is going to go through the circumference and meet up with the tangent outside there. Okay, this inside angle over here, we're going to call x. This inside angle x is going to end up being this angle x over here. Okay, inside the sine. Okay, again, this is radius 1. Okay, so from the origin out to the circumference, that's length 1. Let's put in some points so we can talk about these triangles. So the origin is O, of course. Then let's call this A. When it touches the tangent, we call it B. The tangent point will be C. And where we drop that perpendicular line to OC, we're going to call that D. Okay, so we have O, A, B, C, and D. Everyone still with me? Okay. So what we're going to do now is consider 3 areas in this diagram where we have a smallest area, medium area, and a large area. Okay, so we are going to find 3 areas in the diagram such that the smaller area is area 1, is less than or equal to area 2, which is less than or equal to area 3. Okay, so we have 3 areas, the smallest one, a medium one, and a large one. And I hope you start seeing where we're going to be using the squeeze theorem. So we're going to have f less than g less than h. We're going to take the limit throughout, and we're going to end up with the limit we want in the middle. Okay, so what are these areas going to be? So area number 1 is going to be this triangle OAD. Okay, so triangle OAD, that will give us area 1. Okay. Next, area 2 is going to be this pizza slice sector from O to A to C. So if you imagine you got a pizza with some number of slices, OAC, that little slice of the pizza there, that will be area 2. So the sector or the pizza slice. Okay. Like I said, OAC. So if you imagine that as a pizza slice there, that will be our middle area. And you can see it's slightly larger. So OAD is this triangle here. Okay, you can see that there. OAC, the pizza slice, includes this extra bit. So it's a little bit larger. And finally, the largest area will be OBC. That will be the triangle that goes out to the tangent. Okay, that triangle OBC, that will be the largest area, area 3. Okay, so we have area 1, area 2, and area 3. And we can see that area 2 is larger than area 1, right? Because it includes this little extra bit over here. And area 3 is larger than area 2 because it includes this bit up here. Does everyone see that? Area 1, 2, and 3? Yeah. Now we need to find these areas. So the area of triangle OAD, well, that's pretty easy to do. That's half base times height. So area 1 is going to be half base times height. So this is going to be half. The base is going to be OD. Okay. The hypotenuse there is 1 of the right angle triangle. So the side length OD is going to be cos x. Does everyone see that? The height of the triangle is AD. The hypotenuse is 1. So AD will be sine x. So the area is half cos x sine x, half base times height. Yeah. Everyone see that? Okay, next one. So area 2 is equal to that pizza slice. Now here, we need to put a little warning. Okay, so I said here the angle x. Okay, so in high school, to measure angles, you used degrees, right? You took your full circle, you cut it up into 360. One of those slices you called 1 degree. Okay, think of it like a pizza with 360 slices. One of them has 1 degree. University, we do not use that. In university maths, we don't use that. We use something called radians. So instead of cutting up the circle into 360 degrees, we are going to cut up the circle into 2 pi radians. I'll do a little side note on that. So on radians. Okay, so please from now on, we must use this new angle radians. So for degrees, we took our circle. Let's say it has length, radius length 1. We cut it up into 360 pizza slices. Okay, cut it all up into 360. One of those pizza slices, that angle is 1 degree, right? Because there's 360 of them. Okay, that's degrees. Now for radians, we measure the angle not in terms of these pizza slices going around, but in terms of the circumference. So if it's a unit circle, radius 1, what is the circumference going to be? Okay, no, that's very bad. Okay, circumference of the circle is 2 pi. 2 pi r, but it's a unit circle, so it's 2 pi. Okay, so for radians, instead of this, we're now going to use the following. So let's pick a starting point over there. If we go all the way around, the circumference is 2 pi. Again, it has length, radius length 1. 2 pi. Okay, if we go halfway around, what will that be? Pi, yeah. So here is 0. If we go halfway around, that's pi. So to go between the two, just think of it like this. In degrees, if you go halfway around the circle, that's 180. For radians, you go halfway around the circle, it's pi. What about a quarter? Pi over 2. 3 quarters around? No, we're going 3 quarters around. So we're at the bottom. What's that? No, not dividing by 3. It's 3 quarters. The 4's at the bottom. Someone said it? Yeah. Yeah. 3 pi over 2. Okay. So at the top here, this will be pi over 2 because we're going a quarter way. So a quarter of 2 pi over 2. We go halfway, so half of 2 pi. We go 3 quarters. Now we're at the bottom here. This will be 3 pi over 2. And if we go 4 quarters around, it will be 2 pi all the way around. Okay. You get the idea? Okay. So please, from now on, we do not use degrees. That's baby angles. We don't do that here. We use radians. And we'll see after this example why the radians is so important. Okay. So please keep in mind we use radians. Okay, so area 2 is the area of this pizza slice. Let's shade it in here. Okay, so that pink pizza slice there. What is the area of the whole pizza? Pi r squared. The radius is 1, so the full area is? Sorry? R. No, R is 1. Pi. The full area is pi. So the area is pi r squared. Here the radius is 1. OA is 1. So the area is pi. Does everyone see that? Yes? No? Yes. Okay. So what about this pizza slice here with angle in radians, not in degrees, in radians, x. So we are going X amounts around the full pizza. So in proportion to the whole pizza, we've gone X. What is the full angle going around? 2 pi. So we've gone X out of 2 pi all the way around. So what is the proportion? So we've gone X, the full circle is 2 pi. So the proportion for X is? X over 2 pi. Good. So proportion of the slice is X over 2 pi. Does everyone see that? 2 pi is all the way around. We've gone X, so the proportion is X over 2 pi. Does everyone see that? Yeah. So that's the proportion, right? It's like 1/8 of the pizza, if you want to think about it like that. So what is the area of the slice? It's the proportion of the full pizza, right? So the area of the full pizza is pi. You've got that there. The proportion of that slice is X over 2 pi. So what's the area of the slice? half x. Very good. Okay, so the area of the pizza slice is x over 2. The proportion is x over 2 pi. You multiply it by the full area, which is pi. So the area of the slice is x over 2. Yeah. Fraction. You get your Debonairs pizza. There's 8 slices. I take 1 slice. What proportion is it? 1/8. I have 2 pi slices. I take x. What's the proportion? X over 2 pi. It's, fractions of a pizza. Yeah. Okay. Okay, so area 2 is x over 2. Okay. I hope everyone followed that pizza analogy there. Okay, what about area 3? So area 3, that was this OBC triangle there. So half base times height. OC is? It's the radius. It's 1, yeah. And the height? We've got the hypotenuse, we've got the opposite, we've got the adjacent, we've got all of that stuff going on. What's the height? Okay, 50 points in the next quiz. First person to get the height in terms of x. Yeah? Sorry? Tan x. Son? No. You were next? Tan x. Very good. Okay, yeah, it'll be tan x. Why? Because this is what's this one? Opposite. What's this one? Adjacent. Opposite over adjacent is tan. And the adjacent is just 1. So the opposite is tan x. Okay. Just see me afterwards to get your student number, you as well. So you get your 20%, you get your 50%. Okay, yeah, so it will be half tan x, half base times height. The base is just 1, so we don't have to worry about that. Okay, so we've got area 1, area 2, area 3. Finally, we're going to put everything together and then use the squeeze theorem. Okay, so area 1 is half sine x cos x. This is less than or equal to area 2, which is x over 2, which is less than or equal to area 3, which is half tan x. I'm going to write it as half sine over cos. Okay, we've got a half throughout, so I'm going to cancel it. Okay, here we have x. What we want is 1 over x, because remember, right at the beginning, we were looking for sine x over x. So x needs to be at the bottom, so I'm going to take the reciprocal throughout. Okay, we've got sine x at the bottom on the left and the right. I'm going to multiply through by sine x. Okay, and then finally, for the squeeze theorem, we've got it bounded between f and h. I'm going to take the limit throughout. Okay, so we've set up everything for the squeeze theorem. Now, all we need to check is the left limit equal to the right limit. If they have the same value, the value in the middle is squeezed between the two, so it has that same value. Let's check the left one first. So we have the limit. X goes to 0 of cos x. Okay, think of the cos graph. X is going to 0. Cos x goes to 1. Good. Let's look at the last one. So limit x goes to 0, 1 over cos x. So we can do the limits just at the bottom. Remember limit laws. So a limit of the bottom will be 1. 1 over 1 is 1. So the left limit is 1. The right limit is 1. What's the middle limit? 1. Therefore, the limit as x goes to 0 of sine x over x is 1. By the squeeze theorem, so you can get your part marks. Now, for homework, you're going to do all of this again, but instead of using radians for this step here, where we got the area, you are now going to use degrees. Okay, so I went on the whole thing about radians. If we instead use degrees for this area 2, so the proportion is not out of 2 pi, the proportion is out of 360, then we're not going to get 1, we're going to get, so homework, show that the limit x goes to 0 sine x over x is pi over 180 when using degrees. So everything else is exactly the same, but that pizza proportion is not out of 2 pi for radians, it will be out of 360. Okay, is everyone clear on that? Okay, so please do all of this again, and then over here, that little side calculation, the proportion is not out of 2 pi radians, it will now be out of 360 degrees. So redo all of that stuff, and you'll end up with this as the limit. Okay, and you can see if we use radians, the limit is 1. If we use degrees, the limit is pi over 180. Okay, now you might ask, okay, so what's the difference between using degrees and radians? We don't see it now, but we will see it next week when we do derivatives. So when we do derivatives, we'll see the following, that the derivative of sine x is cos x. That's very nice. Okay, very nice equation. This only works with radians. Okay, if we instead use degrees, we will get the following. This is with degrees. Equation 2 is ugly. We do not want to work with that. Instead, we want to work with this very nice rule that the derivative of sine is cos. Yeah, we can only use that nice equation if we use radians. If we use degrees, we get this ugly equation over here. We want to avoid that. Okay, so we don't want this ugly equation over here. We want the nice one, so we have to use radians. Okay. Now, what that means is from now on, so from this section all the way to the end of this year and next year, we will only use radians. Okay. Now, everyone, please look on your calculators. Okay, just get your calculators. Okay, in the top corner, you'll see there a little D for degrees. Your calculator is probably set to degrees there. Do you see that? Okay, you see the little D there. Okay, now, you mustn't all change it now, otherwise you're going to mess up with Dr. Chetty's work, because he does degrees. Whenever you have a math assessment, from now till the end of MATH161, your calculator must be set to radians. Otherwise, you get 0 for all of it. No, it's an issue because you put in your values. If you use degrees and you're putting in a radian amount, your answer is all going to be wrong. Okay, so you go to your settings. Okay, go to your settings there. And then you'll see there DEG, and then you'll see RAD in your settings. Do you see that? Okay, if you don't see that, just look at your partner. Maybe they'll find it. So you go to your settings, and please look for the menu where it has RAD DEG. Do you see it? Okay. Okay, so he sees it. Hands up if you've got it. Okay, hands up if you don't have it. Okay, do you have it? No. Okay, please can someone who had their hand up please help them? come, someone please go show them. It's a learning exercise. Thank you very much. Please show them. Okay, again, hands up if you do not have those settings, if you cannot see it. You don't see it. Okay, someone up there, please show them. Okay, everyone must have it from now on. I don't want any excuses when we get to the test. You can't say, sir, I didn't know what to do. Please give me part marks. Will not happen. Okay, last chance now. Hands up if you do not have those settings in front of you. All good. Okay, so whenever we have an assessment, including the next one and everything afterwards, at the beginning, you go to the settings and you choose RAD for radians. If you do not choose that, all of your numbers will be wrong when you do the calculations. Okay, so please make sure you know how to do that, especially for this next quiz and everything afterwards. Yeah. Everyone understood? Then, when you go to Dr. Chetty, might not be this module, might be next semester, you do angles of lattices and atomic lattices. You then have to switch back to degrees. You go to the settings and you check you have degrees. Okay, it's a very big problem last year because for Dr. Chetty, everyone had it on radians and they got everything wrong for his section. Then they came to me, they had it on degrees and got everything wrong. It was wrong for both, right? You can imagine the tears at the end of the test. So please, Dr. Chetty's work for the engineering on lattices, degrees. You have to check your calculator. My work, maybe physics, I don't know what Mr. Evans uses, radians. You have to check your calculator, otherwise everything is wrong. Whatever you put in your calculator will be wrong. Okay. Everyone clear? Yeah. And a nice way to check is you go sine of pi, you should get 0. If you do not get 0, you are on the wrong settings. Okay, so if you see the little r for radians, you do a quick check, sine of pi, 0. If you get something else, you're still on degrees, you're going to get everything wrong. Okay, so please change your calculator to radians, put in sine of pi, and check that you get 0. Do you got 0? Okay. Everyone else, you got 0? Okay. So no tears for class test 1, right? You can cry about the other stuff, but not the radians. Okay. Everyone clear? Okay, good. So that will be it for today. Tomorrow we will finish off with continuity. It is the last chapter under functions. So you go to your Stewart textbook. The last section of the limits is continuity. You read that tonight. We go through it tomorrow. Next week, we start on derivatives. That will be the next chapter. Okay. So again, you check your Stewart book here. Okay. So here, functions and limits. You go to limits here. You see this last one here? Continuity. You read that for tomorrow. And then on Saturday or Sunday, you read through the next bit here on derivatives. Okay, this bit here. Okay, everyone clear on the reading that they need to do? Okay, continuity for this evening, derivatives for this weekend. Okay, any questions? All good? Okay, we'll see you tomorrow.